All right. And it didn't share one more time. There we go. All right. Hey, welcome everyone. This is one of our Design Safe webinar series. I think this is the second or third one this season. I'm glad you guys can make it. We're gonna go ahead and get ourselves started. First off, I'd like to introduce myself. My name is whoops, wrong window. My name is Charlie Day. I'm going to be your host. Today's topic is the development and utilization of a relational database in support of the post-earthquake building damage and recovery assessment. Our presenters are Dr. Henry Verburton, who's assistant professor at the and Engelbert Kirk Presidential Chair in Structural Engineering at the Department of Civil and Environmental Engineering at UCLA. With him is a PhD candidate, Maralaki Omwa. She is also with the Department of Civil and Environmental Engineering at UCLA. Before we get started, I would like to give kind of a applause to our NERI Design Safe winners of the 2021 Dataset Award. So this is the first time we've ever done this on Design Safe, and we've got actually 4 winners. First one is from authors M. Gahan, B. Maurer, B. Bradley, R. Green, and Esvan Balagoy. Their dataset consists of approximately 15,000 CPT-based liquefaction case histories compiled from 3 different earthquakes in Canterbury, New Zealand, and they compiled and post-processed the data and published that to Design Safe. Also is from the University of Auckland, a series of experimental tests of large-scale lightly reinforced concrete walls conducted to investigate the minimum vertical reinforcement provisions and form the basis of the revisions for the structural codes, structural building codes in New Zealand and here in the US as well. Congratulations to authors R. Henry and Y. Liu. Hurricane Michael, that I think October 10th, 2018, when Hurricane Michael made landfall just south of Panama City in Florida. Our reconnaissance uh, and the STEER, they uh, sent out a reconnaissance team to do and data collections, and that data collection has also been available here at on Design Safe. And of course, Dr. Roosh, David Roosh, and Felicity Correa, and Berman, Lida, and Gurley, Marshall, Pinelli, Pravat, Smith, Ambrose, Brown, Mohavez, Palmer, Rahafith, Reiner, Daphne, Jung, Grasso, Johnson, and Mongold are the authors on that. You might remember David Roosh actually gave us a talk on his data set here at Design Safe on our webinar series a couple years ago. And then finally, also from Hurricane Matthew, the storm surge and wave simulations from data simulation, with lead author being Taylor Asher. This data set included model simulations and data analysis in supporting study and developing new data simulation techniques to improve our coastal water levels model accuracies. So feel free to go check those out. Those are on our first page of Design Safe, and it's actually kind of cool. And of course, we'll be doing this again for 2022, so keep an eye out for that. All right, of course, Design Safe, we are always trying to improve our webinars and improve our material to make it more relevant to your science. So we would love to hear your feedback on the talk, on the Design Safe in general, our training, what you'd like to see in the future, what you're seeing now. There is the URL for that. There's also the QR code. Just snap a picture of the QR code with your smartphone and it'll take you to the survey. So we really appreciate taking your time. It should only be about 5 minutes or so, and it's all anonymous. All right, so that brings us to today's topic, which is development and utilization of relational database to support post-earthquake building damage and recovery assessment. Of course, our speakers are Dr. Henry Burton and Maralaki Umwa. They have systematically collected and curated some data sets from historical events that provide a strong basis of simulating the physical and functional effects of natural hazards on the built environment. This presentation is going to discuss the development and utilization of a relational database to support post-earthquake damage and recovery modeling of building portfolios. Dr. Henry Burton is assistant professor and the Engelbert Kirk Presidential Chair in Structural Engineering. UCLA. His research is directed towards understanding and modeling the relationship between the performance of infrastructure systems within the built environment and the ability of communities to minimize the extent of the socioeconomic disruption caused by these extreme events. And with him is Morolaki Umra. She's a PhD candidate at the Department of Civil and Environmental Engineering at UCLA. Morolaki I was very impressed to see this. You are very engaged with your community through social media director of the Women in Engineering program and the Minority Surge Fellow and past UCLA chapter president of National Society of Black Engineers. That's really cool of you. Thank you for your efforts. Uh, with that, I'm going to stop my share and I'm going to hand it off to, is it Henry who's going to be sharing?
Yes, yes.
All right, no problem. Let me go ahead and stop my share here. And if you have any questions, please hit up the chat channel, ask the questions there. And Scott Brandenburg and I will do the best we can in answering those. And we'll also curate those questions to bring those to the attention of the presenters at the end of our presentation. Thank you so much.
All right. Thank you, Charlie, and thank you to the Design Safe community for inviting Rolaki and I to give this presentation. So as Charlie mentioned, today we're going to go through a database that we developed related to support post-earthquake building damage and recovery assessment. The current version of the database only has a single event. So the idea here is really just to, and as far as we know, this is the first such database that's going to be put out there. And so the basic idea is really just to start a discussion around what these types of databases should look like. The current version of the database, we don't expect it to be sort of a one size fits all. When it comes to modeling post-earthquake damage and recovery, or even other types of natural hazards, the needs vary quite a lot depending on who's doing the modeling and so forth. So you know, the idea here again is to start this discussion to say, okay, what should be included in these types of data sets? Should we attempt to make a one size fit all, or should we tailor things based on who's doing the modeling? So that's the basic idea behind the presentation, and then we'll talk a little bit about some of the things we've done with the data. So again, I'm Henry Burton, the person who's done most of the work you're going to see here is Morolaki Omoya. And there's been contributions in terms of the database development, as well as some of the research that you're going to see from a slew of individuals whose names are listed here. So this is just an outline for the presentation. I am actually going to pass it over to Rolaki, who's going to tell you a little bit about the development of the database, as well as some of the research that she's been doing on the data set related to Bayesian parameter estimation of recovery-related variables. And then I'll end things off with some additional work that we've done with the database. Rolaki?
Thank you, Dr. Byrne. Good afternoon, everyone. So first, I will be speaking about the process of building a relational database for recovery modeling. So a relational database is a series of interrelated tables that are linked through shared fields called keys, and it actually imposes structure on its contents. And it would be useful for calibrating and validating recovery models. So relational database has a bunch of benefits. It improves the readability of the data compared to spreadsheets, which can be quite bulky. It has unlimited storage capacity. It provides an effective tool to reduce data redundancy, faster and enables faster data processing, and it helps to integrate different types of data from different sources seamlessly. Thank you. So in building a relational database, there are some key terms to note. The primary key identifies a row of data in a table. The foreign key is a link between tables, and it references the primary key of another table. The attribute is an individual piece of data in a table, and it takes a type like the date decimal character, whereas the schema is a combination of tables, attributes, and relationships between tables. I'll be highlighting those also in the upcoming slides. So while this data set contains buildings affected by the 2014 South Napa earthquake, we hope to collect more data in the future about other earthquakes, or at least start the conversation. So this earthquake was a magnitude 6.0 earthquake that happened on August 24, 2014, with PGA as high as 0.6 G and damaging roughly 3,400 structures, with 2,000 structures damaged moderately to severely. And its economic loss ranged from $500 million to $1 billion. So this slide contains the information collected that are grouped into categories of what is believed to affect building recovery. So we know from past disasters that the pace of recovery is affected by the census-level demographics, general building information, and this also lists the sources of where we gathered the data, as well as general building information, the site information, which is related to shaking intensity, the shaking intensity information, which is related to damage. There's the general building damage information that we can use either to simulate or test our models, and building permit information, which is directly input into our recovery model. So here is the schema, which shows the structure of the database. A lot of conversation went into building the schema in terms of what we believed to affect building recovery and also how to arrange this data. So here we have the general building and site properties. It contains the location and salt properties unique to each building. It also has the occupancy type, which can influence permit times, the construction type, which can influence damage, and the general building information that links all the tables. We have the damage assessment information category that contains the shaking intensity information, like source to site distance, spectral acceleration, PGA, which is peak ground acceleration, and the inspection information corresponding to the observed damage, the date of inspection, and also the ATC tags. And like you can see, there's the difference between the primary key and the foreign key. So here in the, let's say the shaking intensity information, we have the building ID, that's a foreign key from the building and site property series. And so here we see that that building ID basically tells us that each of these attributes are actually related to the specific building and also to the specific earthquake. Again, we have the census-level demographics, which contains information about race, education, and income of the building occupants, and that could serve as predictors of recovery. And the earthquake properties, which give general information about the earthquake, its magnitude, the date, the epicenter location. And that could also make it easier to expand the database to include more earthquakes. We also have the recovery assessment category that includes the observed recovery tables with inspection times and the permit information table with the permit description types and also the dates related to recovery. And again, all of these tables, a lot of these tables are related to the specific building and the specific earthquake. Sorry, next slide. So this shows the implementation of the database schema on MySQL, which is the structural query language that we use to develop the database. And here, our data set actually includes 3,695 buildings with 15% more than a century old, 4% constructed since 2000 and to the year 2000, and 67% are single family residency and roughly 11% multi-family residency and commercial. And they're typically wood frame buildings. So after an earthquake, especially one with high magnitude, an inspection is usually conducted by the building department, and ATC 20 tags are assigned, with green tag buildings showing the least damage, and then yellow and red showing the most damage. And here we see that most of the buildings are, sorry, the least represented, which is usual, which is what we expect, is actually the red tag buildings. And in this graph, we see that as shaking intensity increases, the percentage of red tag buildings increases, which will tell you something about the relationship about shaking intensity and damage. The permit and repair information was obtained from the Napa Valley building site for 880 and 672 buildings respectively. The reason for this low number is that not all buildings actually follow up with obtaining permits or report back to inform the building department when they have completed repairs. But these would be very, very important in helping us with our recovery model. So actually the database has been uploaded to Design Safe and it can be publicly accessed using the link below. We're also submitted a data paper as well. And with this database, sorry, next slide, it can be queried. So the database can also be queried, and we have the database publicly available as earthquake recovery database. For example, queries have been published in a Jupyter notebook that's also accessible using the link. And this query shown generates site information for red tag buildings. So it's just a way for you to see that, you know, if you want to query something in the database, it's very possible with the Jupyter notebook, and that just serves as a guide for you to be able to query more things, or, you know, to be able to use the database. So next up, we've spoken a lot about the relational database. So now I'm going to speak a little bit more about how I have used it in building post-earthquake recovery models, and that would involve Bayesian parameter estimation. So we know that recovery models are important, and there are actually various applications for building recovery models, and the importance of them is starting to be recognized more by FEMA, NIST, and NEHRP. So building codes now are based on life safety, and what that means is when an earthquake happens and, you know, hopefully people get out of the buildings alive, but it doesn't really say anything about whether the building will be usable or not. And so now we're starting to think about developing building codes based on functional recovery of the building. And this research is a big step towards that. So overview of the Bayesian parameter estimation. So there are three main ingredients in Bayesian updating. So the data set is one of them, which we have the likelihood and the prior distribution, which tells us the initial beliefs about the parameter. And so Bayes' theorem takes all of that into account using the equation shown and presents an updated parameter distribution, which is also called the posterior parameter distribution. Okay, so the overview of the Bayesian parameter estimation. So basically we use building recovery models. We have one from HAZUS from FEMA, and another model from READY, which is from the Arab group. So the HAZUS gives information about building repair and recovery time, while READY considers the impeding factors before repairs as well as component level repairs. So it gives information on inspection time, permit acquisition time, and repair time, but it's component level repair time. However, because for our data set, we only have information on the building repair time and not on each component level, we would only focus on the first two temporal variables from READY. And then HAZUS and READY then form these two models, and they inform our prior beliefs. And we use this to form a prior distribution. And then we calculate the temporal variable marginal distributions. And from using the data from the earthquake on these temporal variables, we utilize Bayesian parameter estimation. We can utilize the Bayesian parameter updating with the conjugate and also ABC, which is the approximate Bayesian computation methods, to update our distributions. And these updated distributions are termed posterior distributions. And then we calculate the duration variable posterior marginal distributions. And so basically keep in mind that there's a difference between the parameter and the actual duration. So for example, when we have a median, when we're updating our parameters, we're updating the median, but then when we're updating the duration, the actual variables, then we're talking about updating the duration, which is duration-based variables, which is repair time, recovery time, and inspection time. But we'll talk more about that too. So the data set was disaggregated into damage classes based on the different models. And the permit acquisition time is based on the ATC 20 tags, because that's how READY characterizes its own damage. And then the recovery times is based on the HAZUS damage. The repair and recovery times is based on the HAZUS damage states, because that's how HAZUS actually characterizes its own model. Okay. So using Bayes' rule, the posterior or updated distribution, again, is the likelihood of observing the data generated by some models using the parameters multiplied by the prior distribution divided by the multiplied by the prior distribution divided by the marginal distribution. So the table shown below, the conjugate prior approach is used when the sampling distribution and conjugate prior distribution allows Bayes' rule to be solved analytically. And so this usually avoids complex numerical integrations. And in our own particular case, we will be using the exponential gamma gamma because we have an exponential sampling distribution and a gamma prior. Okay. So since we have an exponential sampling distribution and the conjugate prior is a gamma distribution, it can be solved using the updating equations. So, so these are the equations, and basically the prior shape parameter plus number of observations give the posterior shape parameter, and the prior rate parameter plus the sum of observed values gives the posterior rate parameter. And then the mean of the gamma distribution is the shape divided by the rate, and then the standard deviation is the square root of the shape parameter divided by the rate parameter, which is shown in the slide. So the benefits of ABC, which is the second computation method that we'll be using, it includes the ease of simulation models conditioned on parameters, the ease of running many parameters, and it's a likelihood-free approach and allows us to gain insights into which parameter values of the simulated data set best match the observed data. So it's an approximate method. It does not use likelihood function, so it's not a precise model. And we'll be testing the similarity between this approximate model with the conjugate prior approach. And the drawbacks include that there can be a situation where there are few or no accepted parameter values, and these can actually lead to an invalid posterior distribution. So for the ABC methodology, you choose a metric that will be used to compare simulated and observed data. And then you simulate a parameter from the prior distribution. So then you use that prior to simulate artificial data and compare the artificial data to the observed data. And then from there, you either accept or reject the parameter. So the accepted parameter values then make up the posterior distribution of the model. And that would be our posterior distribution. So the marginal distribution is of the recovery assessment variables themselves. So this is not a parameter. So the prior and posterior distributions are on the parameter, whereas this one is actually on the duration-based variables, and is calculated by integrating the PDF of the temporal variable conditioned on a single value of the parameter multiplied by the PDF of the parameter over all the values of the parameter. So these distributions are evaluated numerically, as closed form solutions cannot be obtained in our case. And note that the marginal distribution actually considers the uncertainty in the random variable and also the uncertainty in the parameters. Because there's a distribution. So these are some of our results. So the PDF and the CDF of the prior and posterior distributions are shown. So like we see in this case, the lambda distribution has shifted to the left. So it shifts towards the mean for both the posterior distributions. And then the uncertainty is less for the posterior distributions with the conjugate prior, which is, the most accurate approach, showing which is unlike the ABC is non-precise. So the conjugate prior actually shows the least uncertainty. So in another graph, the completely damaged recovery times are shown, and they also showed very similar prior and posterior distributions. So in the case where it's more similar, it shows that the prior beliefs actually match the data set very closely. So the marginal distribution of the duration-based variables themselves are solved numerically, and we see that the posterior distribution for both the conjugate prior approach and the ABC approach are actually quite similar. And in the next graph, we also see again that for the completely damaged recovery times, there is also similarity. But in this case, it's less similar than the previous one, which this one has a 92.1% similarity at the 1% significance level. So again, these are just some of the results. We actually tested multiple. We tested we did it on a recovery on a damage-based. We did a damage-based approach to the results, and also so it was like about 9 results, and so these are just 2 of them, and most of them actually had very significant similarity between the conjugate prior approach and the ABC approach. So again, so Bayesian updating allows us to systematically incorporate new and different types of data into prior beliefs of recovery time variable distributions. Since we use single family residency and exponential sampling distributions, we actually need further implementation to use other occupancy types and sampling distributions. The building level damage and repair information was the data that we recorded and obtained. So more detailed documentation of the building damage would facilitate application to the component level repair time estimation, which then we can use our ready model for repair time. And it is also worth noting that the repair time from the Napa data is based on duration between permit acquisition and certification of repairs by the building department. So the actual time needed to perform the repairs is likely much less than this duration. So we actually need better markers to be able to document repair duration. Thank you. And that will be all for mine. And now I'll pass it to Professor Burton.
All right, thanks, Rolake. So in the next few slides and for the remainder of the presentation, I'm going to highlight some of the work that we've been doing using different machine learning methods to do building damage assessment. And again, so the basic idea here is to start exploring, are there alternatives given all of the methods that have been developed within sort of the data science machine learning world? Are there techniques that we can take advantage of within the earthquake engineering, within the natural hazards community that either that can improve upon some of our our hybrid models that we currently use to do building damage assessment, or possibly augment those types of models? So I thought I'd start by talking a little bit about how post-earthquake damage assessment is currently done. So as Rolake mentioned, because a lot of the data that we have in that data set is based on post-earthquake inspections, it's usually done in person, where you have the building department would organize a set of volunteers to do these inspections. The inspector would typically document the characteristics of the building and the observed damage, and they would assign a tag based on the ATC 20 guidelines. And as Rolake noted, these tags are usually red, yellow, green, where red means things are unsafe, green means it's safe to occupy, and yellow means maybe there's something that needs to be mitigated before the building can be occupied. We know that this process is a lengthy one. It can take anywhere on the order of weeks to months. So the question that we posed as we started getting into this work is, can we utilize predictive machine learning models to perform rapid preliminary damage assessments of the portfolio, to do things like inform early recovery planning, aid in emergency response, but also enable rapid loss assessments and even inform the sequencing of those in-person inspections. Keeping in mind here, the idea or the proposal is not that the in-person inspections are done away with. These are critical, and there's a lot of valuable information that is collected during these inspections. But it's really just saying, can we leverage some of these machine learning techniques to get better information faster, and to inform some of these earlier decisions? So this just shows the distribution of tags. I believe Rolake talked a little bit about it before. We're actually not using this is not the full data set. It's most of it, but not the entire thing, because we're only using those buildings where we had complete information for. And we use 3 different types of techniques based on the type of data that's used as the features or the input to the machine learning model. In one case, we use characteristics of the earthquakes and the building as the features. And again, these features, when we say features, we just mean the input to the predictive model. In one case, we also use the damage descriptions, and we also looked at using images. I'll only talk about the first 2 because the number of images we had were very limited, so we weren't able to do a lot in this area. So starting with the building characteristics again. So here we're using features such as the spectral acceleration at 0.3 seconds. And again, we're using this particular IM because most of the buildings are low-rise buildings. The board joiner distance, VS30, and then information related to the building itself. So like the age, the number of stories, the value, the plan regularity, and the floor area. We tested several algorithms. I'm not going to go into the details of them, but the ones we tested are quadratic discriminant analysis, k-nearest neighbors, decision tree, and random forest. The random forest algorithm ended up performing the best. And this particular algorithm is one that falls in the category of what's called tree-based algorithms. And what they attempt to do is really just partition the data based on the features such that when you have a new observation, you can classify your observation based on where it falls within those partitions. As with sort of the typical machine learning workflow, we did a training testing split. In this case, we use a 70% for training and 30% for testing. And as I mentioned before, the random forest algorithm is the one that performed the best. We also looked at which features had the strongest correlation with the ATC 20 tag, and we found that the age, the shaking intensity, and the board joiner distance were the strongest features. This figure on the right, it's called a confusion matrix. It's meant to summarize the results, and in this case, we're actually summarizing the results for the test set. And so it consists of, so the columns in this case are the number of predicted classes, the rows are the actual classes. So the various measures that you can use, one measure that you can use is the precision, which is basically the number of, or the percentage of predicted classes that were correctly assigned, meaning the tags were correctly assigned. And then you can also look at the recall, which says what percentage of the actual tags were correctly assigned. And then along the diagonal, that gives you a sense of the overall accuracy. So what percentage of the overall set of tags were accurately assigned. And here we're seeing where we obtained 66% on the testing set. Now, a big question here that we didn't get into, but we hope to in future work is how does this measure up against, say, some of our more traditional methods like HAZAS and things like that? And I think so that's something that we need to look into to really see if there's really any benefits to the use of these machine learning technologies. But again, keeping in mind, in this particular case, we're doing a training testing split, which is something that we're not typically when we benchmark our traditional models, it's not something that we typically do. So we want to make sure that we're making apples to apples comparison when we benchmark things against our traditional methods. As I mentioned before, we also developed a model where we took the descriptions of damage that were documented by the inspectors, and we used those as the features. We used those as the inputs to do the tag predictions. And so the algorithm we use is it's a neural network algorithm. It's called the long short-term memory. It's a deep learning algorithm. We did the training testing split as we did for the previous method. In this case, we actually got much better predictive accuracy. We got 86% overall accuracy on the testing set. But one of the things we realized, or I mean, we knew this going in, but we still thought it was worthwhile building the model. But one of the things we knew going in is that, you know, we're actually using the written descriptions of damage that was collected by the traditional in-person process to do the prediction. So in some ways, we're sort of putting the cart before the horse, because our original motivation was that these methods can give us rapid information early. And you know, one sort of general idea behind doing this written damage-based description is, you can imagine that earthquake happens. It doesn't have to be an earthquake. It can be a hurricane or some other type of natural hazard event. And, you know, people are in their homes. They're able to document what they're seeing in terms of, they're able to write down the damage that they're seeing. Maybe they're able to take pictures and upload to some central database. And then the idea is you would use this information to provide some preliminary estimates on the distribution of damage. Now, again, recognizing that the written descriptions of damage that we use to build this model were actually done by experts, you know, it's not surprising that we were able to get pretty high levels of accuracy on the order of 86%. But one question that this led to was, would you get the same or similar levels of accuracy if you had non-experts doing the prediction, which is the situation you would have if you really wanted to put this into practice. And so that led to a current collaboration that I have with one of my colleagues in the psychology department at UCLA, where and this is someone who is an expert in visual perception. And the question we're asking is, again, can you get, what type of predictive accuracy would you get from the machine learning model if the descriptions are being generated by non-experts? So the experiments that my colleague is putting together is he's planning to put individuals in a virtual reality environment and show them sort of images of damage and have them describe what they see. And then we'll take those descriptions and again test it and then build a similar type of predictive model to see what type of accuracy we get. Now, anticipating that, you know, again, because these are non-experts, their descriptions are probably going to be all over the place. So anticipating that we're not going to get as high accuracy, we can then ask the question: are there things we can do to sort of help target the descriptions that you get from experts? So, for example, would it be helpful to provide, say, like a menu of descriptions that they can choose from to sort of target those those descriptive words? So that's something that's ongoing. My colleague has already done a few experiments, but because of COVID, he's actually done it through traditional computer monitors, and he's actually shown that there is a statistically significant change in the level of in the ability to detect damage from non-experts when you do provide some guidance up front. So that's some work that's ongoing that we're pretty excited about. So to wrap up, I thought I'd talk about some practical considerations for using these machine learning based predictive models based on field reconnaissance data. And so one, we recognize that to sort of enable broad adoption of this type of framework, we need to have development or incorporation into some user-friendly platforms such as Shadecast that was developed by the USGS. Again, here we tested our models against data from a single event. And again, recognizing that, you know, this is one event. One of the things that Rolake talked about was the fact that, you know, the type of buildings that were affected were mostly single family buildings. So it's not a diverse data set, right? So ideally you want to train and test these models against multiple events where you have different types of buildings, different sort of socioeconomic contexts being affected. You know, I talked about before that we want to have comparative assessments of these machine learning models against more traditional methods that use things like fragility. really to get a sense of, is there really a benefit in terms of predictive accuracy? And then obviously we need buy-in from local and state agencies to actually utilize these methodologies. And that's just going to be an ongoing conversation as you start seeing these methodologies start being explored and utilized on a wider basis. Just also to highlight some challenges with machine learning applications in general in earthquake engineering. A lot of these methods were developed with quote unquote big data in mind. And you know, a lot of times the type of data you're talking about is like pixels associated with images. So the sizes of the data sets are orders of magnitude bigger than what we're typically used to dealing with. So it's something that we need to be mindful of. That in our situation, we're typically dealing with smaller data sets. We have to put a lot more effort into making sure that the data is well curated and things like that. And I think design safe platforms like Design Safe, as well as the Rapid facility in University of Washington, are going to go a long way in helping us collect and curate that type of data. We also need to build consensus about what the most appropriate methods are for our field. I talked about the fact that, you know, our data sets relative to what's used in other fields like computer science and medicine are typically smaller, and some methods are more appropriate for these smaller data sets. So that's something that we need to think about. Machine learning models in general have challenges with interpretability. These are challenges that can be overcome. There's various techniques that are being developed to sort of provide more transparency about why you get the predictions you get within these models. There are some algorithms where, you know, you'll probably never get over that issue with interpretability, but there's others where you can get some explanation about why you're getting the predictions you're getting. We have to be careful about overfitting and lack of generality. I talked about the fact that the model we developed is based on a single data set. That's not the type of model you want to go around sort of waving, saying that you have, you know, the greatest model on earth. We want to build models based on data sets that are diverse, based on multiple events, multiple experiments, depending on the type of model, and make sure that we're doing that training testing split, and that the performance on the testing set is not that significant relative to the training set. And with that, I will pass it back over to Charlie, I believe. Or actually, I'm not sure if I'm the one who's curating the questions.
I'll curate some questions. Thanks, Rolake and Henry, for a great webinar. Really interesting stuff. Not surprising, we've gotten some really good questions for you. So I'll go through and read them, and you can decide who should answer which one. I'll just go in order here in which they were posted. So David Bonowitz had a question. If demographics are at a census level, how do you distinguish between demographics of owners who control recovery and tenants, especially for commercial buildings and rental properties?
Yeah, so that's a good question. I think so what David is pointing to, and I appreciate the question, is that we know from prior empirical data on disaster recovery that the pace of recovery is often different when you're talking about buildings that are owner occupied versus renter occupied. We actually did not have that particular type of information. And so that's one type of information that you can say, okay, if we're really talking about informing informing the development of recovery models or just good empirical data, it's a type of information that you'd want to have. But in this particular data set, we don't. But again, the idea here is to really just start this conversation about what should be included in these types of data sets. And you know, is it a one size fits all situation? Should there be multiple data sets and so forth?
All right, thanks. And then next, David Privat asks on the recovery assessment tables. This appears to be one of the most innovative aspects of this work. Would this be some type of appropriate structure that can be published or shared with building departments in order for them to be more stringent in following up with building recovery and increasing the number or data available to be used in the future?
Yeah, that's a great question. It's interesting. So a lot of the data, well, not a lot, some of the data we got, especially the data on the time associated with permitting and repairs and things like that, are collected from the building department. This is specific to Napa. I know not all building departments make this data available, but I certainly think there needs to be a conversation with building departments to sort of, one, share the value of this type of information, maybe talk about how it's used within the researcher and practitioner community, but also share tips and ways in which the data can be organized that maybe it can be easily made available to to the research and practitioner community.
All right, great. Next, I think you may have answered this one, but I'll ask it. I think you showed some slides showing green tag buildings after, but please clarify, did you also database undamaged buildings with similar attributes which are necessary for calculating fragilities?
Yes.
Also, many buildings experience downtime without needing a repair permit.
Yeah, so great question from David. So David is basically pointing out, and this is David Bonowitz, David is pointing out a lot of the information that's not in our database, which it would have been great to have. And I think, and so the answer is no, but again, just to provide some context, I think what David is trying to highlight here is one of the practices that needs to be evolved in terms of when we do our post event inspections. Especially as structural engineers, we tend to run towards the buildings that are damaged and collect all the information on those buildings. But as David is highlighting, it's really important, just as important, to collect information on buildings that are not damaged to be able to develop these damage fragility functions.
Yeah, it's a good point, Henry. Nobody ever runs out and takes a photo of the thing that didn't happen after an earthquake, right? All right, thanks. So next, Sean Adi asks, I really appreciate the effort and development of relational databases from scratch for specific studies, i.e. for the South Napa earthquake. I'm wondering, did you reinvent the wheel for your ground motion / earthquake catalog database design and schema, which existed in similar forms already, NGA, NGL, the UCLA shear wave velocity profile database, USGS products, et cetera? And was there a collaboration in this development?
Yeah, so good question, Sean. So in terms of reinventing the wheel, one of the things that's important in developing this type of database, we're trying to link information on shaking and soil related information to the level of damage, right? So you could sort of argue, which I'm not sure if you're doing that, well, that information is already with USGS and things like that. Well, the information on the shaking or the VS30 is with USGS, but it's not really tied to the buildings themselves. So I think there's value in creating a database that has that information housed in a location where it's associated with the buildings. In terms of, maybe there would need to be more coordination with organizations like USGS when developing these types of database, just to make sure that the information we're sort of collecting and curating is sort of in line with what they have. I think that's a good strategy. But I think it's good to have, even if there's a duplication of some information, I think it's good to have this information in one place in terms of the shaking, the damage, the recovery, things like that.
All right, the questions are still coming in. This is great, very active crowd today. So David Privat asks, great work to the authors. I would be really very interested in hearing about your conclusions, also expressed in a manner that the residential community can comprehend and act upon. Given that you've obtained this data from the building department, it would be important for engineers to work with the potential users of the validity of your modeling. Can we base your data set when 50% of all residential structures are restored to use? Second, how would another researcher be able to use your data, say for another community nearby?
Yeah, so the first question, can we base on can we base on your data set when, yes, okay, I think I understand both questions. I think the questions are related. So I think what David, and this is David provide in this case, is asking, what if you have a situation where the extent of damage is much more significant, or just a different set of characteristics of buildings in general. And so I think if I can sort of try to put my perceive what David is asking, he's pointing to this issue of generality or generalizability of data and models. And I talked a little bit about this before, in the sense that you have to be careful as modelers. When we develop a model, we have to be careful and honest about sort of what is the basis of our model, how general is the data that goes into our model, what are the model assumptions, and I think it really points to the need for having additional events incorporated into this particular data set before we can say anything about its generality. Yeah, I think that's what David is getting at. But
all right, thanks, Henry. And then the next question's from Abdul Salman. How did you decide on the socioeconomic indicators to include in the data analysis?
Rolake, you want to take this one? Sorry, not to put you on the spot.
No, it's okay. Yes. So how did we decide on socioeconomic indicators to include in data analysis? So I said this before, but we basically looked at the socioeconomic factors that we felt like would be good predictors of recovery. So based on the census level data. So we talked about race, we talked about education level, who owns the building. So is the owner, is it a rented property or owned property, the income of the family? So basically just what we believe that would influence or we've seen in the past that would actually be good indicators of recovery. So I don't know if that answers the question, but yeah.
Yeah, well, I think I think the last thing you said there, I just want, if I can just sort of emphasize that, which is that it's based on observations of past disasters, right? So basically what we did is we went through the literature and we looked at, because there's been a lot of literature on sort of empirical data on past disasters and trying to look at trends in terms of what affects the pace of recovery. And so a lot of the socioeconomic variables that we collected are those that we've seen from past literature that tells us, okay, these are things that affect the pace of recovery.
All right, thanks to both of you. The next one I'll ask is by Yasaman Zainali. Thank you. What was your data collection resources?
Our data collection resource. Okay, so I assume Yasaman is meaning where did we get the data from? So it was various sources. So I mentioned before that all of the information on the duration-based variables, meaning how long did it take to get a permit, to do repairs, those are based on the building department. The damage information was actually obtained from the ERI clearinghouse, and we got permission from them to sort of create this database and utilize it. The sociodemographic information, a lot of that came from the census. Yeah, and I think that's the main types of, those are the main sources of the data.
All right, and now there are quite a few questions here about machine learning too, which came in toward the end of the talk. So the first one from Yajao Shi, are there any suggestions to tackle those machine learning challenges that you outlined?
Yeah. Well, okay. So, I mean, because, we can talk about this all day. So in the interest of time, I'll just pick one or two. So in terms of the data sparsity, I mentioned before that, platforms like DesignSafe, centers like the Rapid facility, which is sort of geared towards going out and collecting the data, whereas Design Safe is more sort of on the curation and storage of the data. That is going to go a long way towards collecting additional data. You know, there needs to be a curation process so that we make sure the data is of good quality. So maybe there needs to be a little bit more done there on the curation. In terms of pick one more, building consensus on the most appropriate methods. You know, when you look at a lot of the papers that have been written, and it includes some of our papers, it's a lot of situations like I talk about today where you know, the modeler would try different models, and then at the end they would say this one worked, which is essentially what we did, right? So obviously I'm not pointing any fingers here, but I think there needs to be a more concerted effort to sort of document why we think a particular model worked versus the other, so that the next person doesn't have to try every single model. So I'll leave it there in terms of two things that can be done.
Right, great. We have two kind of related questions about how to decide on what goes in the training and what goes in the testing data set. So the first one from Omid Sajedi from University of Buffalo. How do you split the data set for training and testing? Is it random, or do you follow a certain logic to evaluate the generalization capacity of your data-driven models? And then also related, Sajang KC, for a large data set, more than 100,000, varying over large geospatial area, how do you split the building data into training and testing data?
Yeah, so, well, I think in terms of, for both questions, the split, it was done randomly. One of the things that we did not show is that we actually repeated this process multiple times, meaning the random splitting of the training and testing, and we would refit the model. And so we actually could obtain a full distribution on the classification accuracy. And one of the things that we were able to show is that the dispersion around that accuracy by doing this random training and testing split is actually kept pretty small, especially for the random forest algorithm.
All right, thanks. Charlie, let me know when we need to cut off questions for the sake of time. We still have 4 more, and I'll proceed with asking them until I hear from you. So Sylvia Mazzoni has a great question. How do you have access to insurance claim information?
Hi, Sylvia. We did not include any insurance claim information in this particular data set, no. That information is usually pretty difficult to come by, and when you do come by it, which we've done for other events, a lot of times there's issues with sort of privacy and things like that. That means that you can't really put it out there.
Okay, and then David Bonowitz says the idea of remote tagging is really interesting, but I suspect the problem it solves is not the lack of an expert, but the expense of getting experts into the field and the time it takes to go to the site. And he says also guidelines for tenants about what images to collect and upload would be very useful. So it's not really a question, but I just wonder if you have a comment to follow up on his comment.
Yeah, well, for one, I didn't really say there's an issue with the lack of an expert. I think the issue I was trying to point out was that if we're trying to use these things in the context where we're trying to get good information quickly, meaning within, you know, hours of the event, then you have to talk about relying on sort of non-expert citizens, citizen scientists, if you will, providing that information. So that's something that we have to be mindful of.
All right, great. And then there's a good question too about feature selection for machine learning from Ali Hassanzadeh. So, hi, please clarify which parameters should be considered as input parameters in machine learning for the prediction of building rehabilitation. Some of the input parameters are dependent on each other, and therefore it's very important.
Yeah, good question. So building rehabilitation, I'm not sure where the rehabilitation term comes in, but in terms of in this case, predicting damage, which we were trying to do, we started with those features that we have been traditionally used in our predictive models. So in things like fragility parameters and things like that, those things are based on things like spectral acceleration. The person brought up an important point about sort of the correlation across features. So for example, here we actually used the spectral acceleration at 0.3 seconds. We also use the ball joiner distance. You can argue that those two things are correlated. And there are some models where the correlation across features does actually create a problem. That is not the case. But those are the more sort of traditional regression models. In models such as random forest, the correlation across features is not really an issue. So it's really just a question of, it becomes a question of, does an additional feature correlated with others or not, does it improve your predictive accuracy? I think that's the question. That's the question you want to ask. If you were doing something like, say, ordinary least squares, then correlated features, multi-collinearity becomes a problem. But when you're working with things like random forest, that's really not an issue. The other thing I want to point out is that I mentioned we use features that are sort of traditional to our engineering models, that have been used in our engineering models. We also use some that were pretty unusual. So for example, the value of the building. You might ask, well, what does the value of the building have to do with its vulnerability? Well, it turns out that the value of the building is actually a good proxy for how well the building has been maintained. And there's other studies, I believe, Professor Hussam Mahmood in Colorado State, who's done some work in this area, but I believe for predicting hurricane damage, where he showed things like the value of the building can actually be good predictors of damage.
All right, so there is one more question. I know we're 1 minute beyond already, but this is a really good one. So I think I'll ask it, and hopefully people don't mind sticking around a little bit longer. So David Bonowitz has a good question about whether it would be useful to develop a test bed in advance, a database of information that's more detailed than what's available from the building department in advance of an event that might be trained once those event parameters become available.
Yeah, well, so there are some of those test beds that have been developed and are being developed, for example, by the NIST Center of Excellence. I think the question you have to ask is, if you're developing a test bed where you're sort of making up data, so to speak, you have to ask, if you're training a model on data that isn't necessarily real, then you have to ask sort of, how useful is the model? Now, as I'm sort of talking and thinking here, maybe what David is referring to is maybe we should be starting to collect some of this data that we know will be useful ahead of time, right? So maybe not things like the shaking intensity or the ball joiner distance, but information on BS30, building age, number of stories. I think having all of that information sort of curated and collected ahead of time is certainly a good idea. Yeah, so I'm looking at David. He responded in real time. Yes, he's referring to real world test beds, and yes, I absolutely agree that creating these real world test beds where you have this information ahead of time is certainly of value. I think you'd have to convince someone that even without an earthquake, it's a value to sort of pick a city and sort of collect all that information and have it well curated and collected.
All right, great. Thanks again, Henry, and thanks, Rolake, for a great presentation. I think I'll, oh, there was one more question about whether the webinar has been recorded and will be posted, and the answer is yes, it'll be posted to the Design Safe website, and I'll hand it back to Charlie to close it out. You're muted, Charlie.
All right, sorry about that. Hey, thank you so much, Henry and Rolake. That was actually really cool information. It's a great approach, and I'm glad to see that the community was engaged in your material. Thank you so much for presenting today and being part of Design Safe. So somebody asked, hey, are these recorded? Yes, they are. If you go to Design Safe's training archive, you'll find all of our previous webinars recorded there, and you can go to our Design Safe YouTube channel. As soon as these videos are curated and set to go, we will publish those to our YouTube channel and share them on our Design Safe training archive. So thank you very much. Finally, again, here's the link to the survey. Please, I would love it if you guys took this. It takes about 5 minutes. It's all anonymous. So we can bring you great webinars like this in the future as well. Thank you so much. And once again, thank you so much, Henry and Marolake, for your presentation. It was very much appreciated. We really appreciate your time and you all sharing with us on this Friday afternoon. If anybody has any other questions, feel free to email us at training@DesignSafe and we'll forward your questions on. You can also, of course, find us on Slack and ask your questions to the general channel, and we'll make sure the questions get to the proper person. With that, if there's anything else, feel free to ask your questions now. If not, find us on Slack or email us at DesignSafe. If you have any suggestions for any future webinars, any ideas, or if you'd like something that you'd like to present, feel free to contact us as well. That'd be great. And with that, thank you so much for joining us. Thank you so much again, Rolake and Henry, for being here today. Everyone have a great weekend and stay safe, and we'll see you next time.